Hello, everybody. My tea is very hot today because I just poured it. Welcome back, everybody. It is day 8 of Advent of Code 2024 in Kotlin. It is a Sunday. So, thank you, everybody who decided to spend a little bit of their weekend with us today. If you are in chat, whether that's on YouTube or on Twitch, please say hello. And you know the drill by now. How'd you feel about today's puzzle? Do you enjoy working with some 2D grids, perhaps? Maybe some collections of vectors or some sets? Who knows? I did today's puzzle on slightly less sleep than usual, because we did have our Christmas party yesterday. But I feel like I still prevailed. It's all good. I always do get a little bit nervous on the weekends, especially, because you never know when Mr. Eric Wastel decides, hey, people probably have a little bit more time. Might as well make this a little tougher. And here's something that I can very much empathize with. It was nice, but it was not clear from reading it the first time. And the definition of anti-nodes was a bit confusing at first. Yep, the text was a bit confusing. Messed up the definition at first. Yep, reading the description was confusing. But surprisingly, it worked first try. I think that's a bit of a pattern for today. There's a couple of sentences that I stared at for probably a good, 4 minutes before trying to build something. And I mean, this might be a little bit of a spoiler, but at the end, I just kind of looked at the image and tried to figure out where exactly to place things just based on the image. I had to look up the formula to find the third point that are collinear to the first 2 points, but everything else was easy. Interesting. I guess we'll maybe see a couple of different approaches here as well. Not a clear description today. Lost 30 minutes because I was debugging part 2, and all I needed was to remove a drop 1. Yeah, it's tough. I'm not sure if any of you have watched Eric Wastel's keynote that he gave. Can just pull that one up again here for a second, which is the following video, which is this video. Advent of Code behind the scenes. And Eric apparently has a whole bunch of people who test the puzzles before they go out, which makes sense. You do some sort of quality assurance. So when a puzzle comes out and I get super confused by the description, I do always just wonder whether it's me, whether it's a thing with speaking English as a second language for myself, or what's up. Yeah. Text was impossible to understand. Had to go with the example to find the pattern. Yep. But that's the one good, the one very good part about Advent of Code is that they do have a bunch of examples that typically help you. Sometimes you'd wish they maybe have some slightly more edge case coverage, but they're pretty good. I think his testers are mathematicians. That may well be the case. Oh, by the way, look, it's us down here in the corner, live. You're on the big stage, everybody. Yeah. So once again, thank you so much for tuning in. Before we dive into the problem, you know what comes next. We have an entire campaign around Advent of Code 2024 and solving a couple of problems using cool JetBrains technologies. That's Advent of Code 2024 in Kotlin. You can win prizes. There's an entire blog post around it. So if you haven't checked that out yet, please head on over to that blog post, because there's Leaderboard that you can join where you can compete for a top spot. Or if you don't want to compete for a top spot, just being in a leaderboard means you might have the chance to be lucky and get some prizes. And of course, there's also a way of winning prizes by tagging your repository on GitHub with the topic AOC 2024 in Kotlin. And if we take a look at that, we can see that we've had a growth of another 33 repositories since we last checked in, at 833 participating repositories. Very exciting. You love to see it, that especially even after all this time, there's still people either starting or adding the tag. And of course, those folks have a chance to win a couple of goodies that are exclusive to Advent of Code. And of course, this is also a great way to discover our templates. We know how that goes. DevTechnica asks, can I tag my Gleam solution repository with AOC 2024 in Kotlin and win the prize anyway? This is not like an automated drawing. Like, we'll get this data and we'll do like a quick like validity check. But you know, if you have a mixture, if you do some Gleam solutions and you also try a little bit of Kotlin, then yeah. I think the blog post specifies, as long as you have 3 Advent of Code puzzles in there that are solved using Kotlin, you can solve whatever else you want to do in something else. But maybe, just maybe, you might find Kotlin so enjoyable that you continue doing it for the rest of the Advent of Code. Who knows? But today is a bit of a special episode anyway, because we're going to be branching out a little bit from Kotlin. It's not just going to be it's not going to be Gleam. Sorry about that one. But we are going to look a little beyond our regular horizon, I should say. In German, you say beyond the rim of your plate, which I struggle to come up with a good analog expression in English, but you get what we mean. We're looking at the color of the grass on the other side of the fence. And of course, we're not going to do that alone. I'm going to do that together with my lovely guest. So I'm very excited to introduce to all of you Vitali, who is one of the developer advocates here at JetBrains. Hey, Vitali, how are you doing?
Hello, I'm good. Thank you for having me here.
I'm so excited to have you. Do you want to give you like a brief introduction about yourself? Maybe like how much of Advent of Code you've done yourself, and what it is that you spend most of your time like writing in?
I think I'm solving Advent of Code problems for maybe 4 years. So I enjoy that a lot. Like I don't I usually use Rust, because at JetBrains I mainly work as a developer advocate for Rust. But I did once in Haskell, I did once in OCaml, so I like to experiment with languages. So this year I've solved all the problems so far. Hopefully I'll be able to solve more. I'm not sure. You never know.
Yep. That's very true.
Yeah.
So this is a great thing to shout out here. Of course, first of all, because I think there's a natural story for at least some folks when it comes to actually the combination of Kotlin and Rust. If we look this one up, there's just at KotlinConf recently, there was a talk from somebody from Mozilla about crossing the barrier between Kotlin and Rust and back, which is quite cool. And when we talk to people, we oftentimes have situations where if they need like a highly performant or like a systems level part of their larger application or SDK, you sometimes find people writing that in Rust and then creating Kotlin bindings so that people can use those from their apps, for example, or just have a convenient way of working with it in an application level language. So for that reason, I think alone it would already be great. But there's more, right? First of all, there's a blog post on the Rust Rover blog, which is our IDE for working with Rust that we'll see later. Vitali, do you have a short TLDR of what the content of this blog post is?
Well, I should say it's pretty the same one as you described, but for Rust. So we also have a template repo, and we have leaderboards. You can join them, you can participate. So yeah, I created that template. I used that one myself. There is also one other blog post actually describing the rationale behind this repo, and I also came up with some recommendations if you want to try solving those problems. Yeah, that second one. I like the title, Advent of Code in Rust for the Rest of Us, because like there I'm writing something about like this whole idea. Why do we solve Advent of Code puzzles? Because like I am not a competitive programmer.
Yeah,
I never make it to leaderboard. So, but I still enjoy it. Maybe when I present my solution, maybe I'll tell you more about my advice on how to approach Advent of Code puzzles.
That sounds amazing. Very much looking forward to that. And one of the other things I think that is worth maybe talking about very briefly right from the get-go is that anybody who hasn't heard about Rust Rover yet, if you pull up the actual website, you will first of all see an ad for this very stream. But there's also something else. Which is that there's this wonderful tag here, which says that Rust Rover is free for non-commercial use, which is pretty cool.
Yeah, so if you want to learn Rust, then just go ahead, download Rust Rover and start using full functionality without any limitations in Rust Rover. You don't have to pay. It's free for non-commercial use. That's right.
Yeah. So there's a lot of things, and we'll see a little bit more about that later on. Of course, we'll see a little bit of Rust Rover in action. But first of all, so we're gonna change the structure a little bit. I'm going to be presenting my solution first, so that everybody who presumably has done a solution in Kotlin, has something that works with their immediate context, and we're kind of all on the same page. And then from there, we'll dive into what Vitali has prepared, and hopefully that should give us a pretty easy understanding of what's going on, both in the Kotlin side and on the Rust side. So I'm quite excited. The hat, of course, as usual, goes on. And
I don't have a hat, this hat, unfortunately. So sorry about that.
That's okay. Don't worry. It does help with solving the problems, though. At least so far, I think. Like, so I've worn it every day, and I've managed to get all the stars so far. So I'm clearly seeing at least a correlation. Okay. So we are starting today with day 8, resonant collinearity. Collinearity? That's a lot of L's. You find yourselves on the roof of a top-secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter, or digit. You create your map, your puzzle input of these antennas. For example, we have a couple of antennas that are marked with a 0, and we have a couple of them that are marked with an A. The signal only applies its nefarious effects at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. We'll talk about that one in a sec. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So, for two antennas marked with frequency A, they create the two antinodes marked with a hashtag. Okay, we'll try our hand here at interpreting this sentence again. An antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. So for this for this antenna and this antenna, we create an antinode because it has two antennas that are in line, and one of them happens to be twice as far away as the other. So looking from the perspective of the antinode, this one is like, well, it's like 2 down and 1 over. And then there's another one which is 4 down and 2 over. So we have a pair of antennas that create this antinode. And then for the other side, we have the same kind of pattern. Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map, so instead it only adds 2. So once again, we have these 2 being responsible for this resonance. We have these 2 being responsible for this resonance. We have these 2 being responsible for this resonance, and we have these 2 being responsible for this resonance. Which, as we can very clearly tell, reuses a bunch of them. Antennas with different frequencies don't create antinodes. A capital and A lowercase count as different frequencies. However, antinodes can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes, but has a lowercase a frequency antinode at its location. So that's because we have these 2 antennas that create an antinode here. It's just not marked because there's also an antenna here. The first example has antennas with 2 different frequencies, so the antinodes they create look like this, plus an antinode overlapping the topmost A frequency antenna. So again, we can kind of, I guess, take a look here. If we have this one and this one, it creates this antinode. If we have these 2, that it looking at them from this direction, it creates this antinode. If we look at them from the other direction, it creates this antinode. And then we have a couple of ones that are also like higher distance. So we have these 2 that create this one, and also in the other direction. And we have a couple more on the diagonals as well. Because the topmost A frequency or capital A frequency antenna overlaps with a 0 frequency antinode, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many unique locations within the bounds of the map contain an antinode? Ooh, okay. Vitali, I am going to jump into my solution just a little bit, but I do want to hear your opinion on the problem and what went through your mind when you first read this, saw this, all of that.
Well, I usually try not to read, because when you read, you get scared pretty quickly, and then like it looks like the author just drives you away from the actual task at all times. So that's my feeling. So I am trying to understand by looking at the puzzle input, at examples, and then maybe and then look, and then I might get some ideas, and then I try to implement them, and if those ideas work, then I'm lucky and I don't have to read carefully. Right? If my ideas don't work, then I start rereading those texts, try to understand what's going on, why my idea doesn't work, and then and in that case it takes just a lot of time to fix everything. So first I try not to read.
It's a good move, and I think people very much agree with you here. Yeah, Vitali is on point, and yeah, it does sometimes help not to read every sentence too often and get too locked in, which I think is very true. I do like Maya's approach, saying I stared at the floor tiles to know the formula for the anti-nodes today.
I have a confession to make, right? So I have a very deep mathematical background. So I'm like one of those testers for Advent of Code. So for me, it was easy this time because like this word collinearity in the title, I know that word. So it's
Is it always spelled with a double L?
Yeah, I think so.
Wow. Okay. Interesting. Yeah, maybe Googling this would have been useful in the morning. now that I think about it. Okay, but we'll see, because I did not Google it, and I still came up with a solution. So we can kind of take a look at that. So the essential thing, just by looking at the input, or well, also by reading the entire novel that surrounds it, was the first observation was the characters of different characters don't really interact with each other. All the like zeros interact with each other, all the A's interact with each other, but apart from that, you're kind of just trying to figure out how those subgroups specifically interact with each other. The other part is that this does not even become relevant for placing those antinodes. Right? The antinodes can just sit on top of an antenna. That is also something that I think was pretty easy to realize. The other part that I thought was so important, because I knew I was going to forget it, that I put it into a comment that we'll see in a little bit, that just said, don't forget to cut off the things that are outside of the map, is that the map constraints are actually relevant here. You can't create antinodes outside of the actual grid that is given to you. And then apart from that, it just by looking at all the pictures, it seems that the overall approach is something like, take a look at any pair of elements that happen to share the same letter, then calculate the vector between those two. So essentially just subtract the two coordinates from each other, multiply that by 2, which gives you like a direction vector, which is longer, and then add that back to the position of the original element, which gives you the offset, like actual vector to point you where the antinode exists. And then it's a little bit of data structure wrangling to make sure you actually look those up reasonably fast, and make sure you don't hit duplicates too much. Sound good so far, Vitali?
Yeah, absolutely.
Okay. So with that, let me actually jump on over here into Fleet, and we can take a look at my solution for this. I can see there's some vector math involved. The vector2 class comes out again, but once again, freshly crafted just this morning at like 6:07. At some point, I should learn how to use copy and paste, but this time we can see there's a new operator that I needed anyway. Yeah. So, first of all, again, we have this wonderful story about our line indices, right? Because we need to figure out how big our map really is. So I just decided I'd grab the map X and Y range. And then I was like, well, the first and most important part is being able to look up elements based on their type. So the capital letter, lowercase letter, or number that's associated with it, and return that position, which I have down here. I'm not quite sure why my navigation is not working. Let me just reopen this file and see if that fixes it. And if not, I'm just going to do a quick smart mode toggle. But anyway, we have the code right here. So this lookup is pretty simple. Essentially, all we do is we loop through each character, and if that character happens to be a dot, that's an empty space, we can just continue. Otherwise, we create ourselves a two-dimensional data structure, which is essentially a map for a given character to that specific position. To all the positions where that specific character occurs. It's a set because they're unique, and I don't care about the order. You can see that while I'm using a bunch of loops in here, I'm still actually using something from the Kotlin standard library, the build map function, which is one of our lovely collection builders. So this function essentially just gives me a lambda, and then inside this lambda, I could call anything that I could do on a typically mutable collection, and then still create a read-only collection at the very end of it. So you can see I call like this.put, or I guess we could just do an assignment. This is all happening for the map that's being created as part of this function. So this is just the input parsing. There's nothing particularly special here, but now I have a way of figuring out, given a character, where do those characters appear. And with that, we can solve our part one. My part one takes two parameters. First of all, that lookup, and then the second one is just an is in bounds check, which just, again, I pass that in to make sure I don't accidentally generate something, an anti-node out of bounds. How do I do this? Well, the answer is a bunch of loops. First, we have a bunch of different antenna types. Those are the keys in our type to position array. So we'll just, or our list, sorry, our map. And we can just iterate over each one of those. And then we do the typical thing where we want to do pairwise iteration, which is we just do two nested loops. We first grab ourselves the first element based on that antenna type, and we also iterate once again through the same thing for that specific antenna type. If we happen to pick the same two things, then we can't really do anything. There's no real like comparison that you can usually do, so we'll just continue. So now we have a loop body that is always differing pairs of antennas of the same type. And from here, we do this tiny bit of vector math. And here, I guess I can very briefly, for folks who need to brush up on this just a tiny bit, we can pull up the TL draw here for a second. And we can say that for, like, if we have two, let me just see here, I'm not very good at this. If we have 2 points, and those points are described by some vectors, those typically come from like your coordinate system, right? Oh my god, I should probably, yeah. You can tell I'm not Dave Leeds, who's a little better at drawing this. We have one vector which describes this first point, and we have another vector which describes that second point. And what we're really interested in is finding this orange vector between our 2 points, and then being able to multiply that by 2, so that we can find that point where the anti-node is then finally created. So the math for this is just something that I still remember from university, which is if this vector is called A and this vector is called B, then this orange vector in the middle is B minus A. And vectors are like, you subtract those component wise, so it's literally just second minus first. This is the minus, so we do x minus other x and y minus other y. Nothing particularly wild here. And then to get to this longer vector, which I should probably just make purple to make this a little better. This one is just 2b minus a. So that's just the same vector scaled. And scaling a vector is also just done component-wise, as long as you do it with another scalar. So if you just have an individual number, we just do that component by component, and we get that vector. What we do notice, though, still is that this purple vector is not yet does not yet come from the origin of our coordinate system. So we still need to offset it by the red vector describing A. So our final thing that we have is our A plus this 2b minus A. That gives us the actual coordinate in the grid system. Let me know if that was at all useful or just a lot more confusing out there in the chat. Was it at least correct, Vitali?
Well, yeah, I think it's absolutely correct.
Great. I am glad that there are some like vague memories of linear algebra still floating around up there somewhere. Once you've done that, you've
by the way, Seb, do you think that it's unfair that you can use your like university knowledge while solving advent of code puzzles? Because in many cases it's the case, so it really helps, but maybe it's unfair. What do you think?
That's a good question. I don't know. I feel like if I didn't know this, I would not fault someone for Googling it while solving this. Like I feel like Googling is very much allowed if you don't know where to go next, because the entire point is to learn something. But yeah, I mean, of course, it made it a little easier here. But yeah, so now the last thing that we just need to do, this is just the math that we just did. We just need to check that we are still in bounds, which again, I did this using a little bit of bonus Kotlin functionality. I made this parameter to this function a lambda with a receiver type, which just means I can call this function as if it was a member on vector2. This is just me showing off. And I could also just have this as a regular function of like vector2 to boolean, and then you just need to have the regular calling convention. So it's really just about making this small aesthetic change. And when you've done that, you just put all of that in a set. Why do we put it in a set and we don't just put it in a list? Because we have multiple ones of them, and they might overlap the same grid cell. And in that case, we don't want to double count them. And with that, we have a solution. Like that's pretty much all there is to it. We count how many of those. Oh, we had a slight mishap up there. All we need to do is execute this and then count how many elements we have that happen to be anti-node locations. And when we run this, which I can actually very briefly do, we can see that, give this a second, compilation is pretty slow, but the actual run speed, it's like 5 milliseconds. Like this is not, it's not that bad. And this is on the actual input, which, by the way, also a good idea to look at before you write the things. is not that huge. Like, the number can't conceivably become that large, which which is also always very nice. Okay, Vitali, should we go straight into the Rust solution from here, or should we also just briefly take a look at the second part? What do you think is better from a teaching standpoint?
I think let's look at part 2.
Okay, let's do that, and I feel like that's not gonna keep us away for too long, because I am excited to see what this will look like in Rust, and whether you have as many nested loops as I do. Let's also just take a quick look here. Drawing a line with equivalent points, with equidistant points, is grade 5 to 6 stuff. Okay, that's, I guess, a good answer to also whether it's university knowledge that I'm using here. Yeah, take the difference from A to B and add it to A. Okay, yep. So I'm glad that more people are comfortable with doing a little bit of arrow drawing and a little bit of a teeny tiny bit of math. Okay, so we'll take a look at part 2. Watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonics into your calculations. Whoops! After updating your model, it turns out that an antinode occurs at any grid position exactly in line with at least 2 antennas of the same frequency, regardless of distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. So these 3 T-frequency antennas may now create many antinodes. So we have these 2, which now create these 2, and then we have these 2, which happen to just kind of like, well, it's like almost at every, like, it's in an equidistant, so at the same distance, we get more and more of these, I guess, until we run out of map. In fact, the 3 T-frequency antennas are all exactly in line with 2 antennas, so they are also all antinodes. So I suppose given these 2, this one is then also an antinode, for example. This brings the total number of antinodes in the above example to 9. The original example now has 34 antinodes, including the antinodes that appear on every antenna, which looks like this. Calculate the impact of the signal using this updated model. How many unique locations within the bounds of the map contain an antinode? Okay, for this one, I'll be quite honest with you. I took a brief look at my drawing, and I identified the part that was double the size, which is the 2, and I thought to myself, this can probably just be generalized. All I gotta do is figure out how to do it in the constraints of the map, somewhat conveniently. So, yeah. I mean, I don't think there's much discussion that we need to do here. We can just jump straight into my part 2, which is subtly not in any way refactored or anything, but just does exactly what it says on the tin. Instead of just picking out the location that's 2 times as far away, instead what we do is we calculate the next location by taking our fun little distance vector that we created beforehand, which I just lost in a different tab, but I feel like we've all understood it. And we just continue adding it onto our value while we're still in bounds. So we just do that, we add it to our collection, and then, because at this point I was like, I mean, it's plus and minus, but I can't be bothered to now start parameterizing things or start doing something there. I'll just run the entire same loop in reverse as well. So it's just the exact same thing. This time we're subtracting the relative distance vector, which means we're walking in the other direction step by step, and we're adding all of them to our collection. And we do that as long as we're in bounds, and we cancel out afterwards. And
by the way,
yes.
Seb, at some point while I was solving this puzzle in Rust, I tried to use do while loop, but unfortunately there is no such thing in Rust.
Really?
Yeah, so you need to figure out how to do something like that. It's not that easy.
Okay, that does sound a little tricky. But yeah, so the entire solution now, if we run it, again, the second part, ironically, even though it does more, runs a little faster. I am pretty sure that this is due to the just-in-time compiler starting up, because if I wrap this entire thing in like 100,000 repetitions. Actually, first of all, let's do it with 1 repetition so that we have a baseline again. Our baseline happens to be 4 milliseconds and 1 millisecond. If I happen to run this same operation 100,000 times, gonna give that just a moment. But we can already see that the very last digits, those are now microseconds. So after, and this is the beauty of being on the JVM, without changing anything else, our algorithm, at least in this case, with the same measurements, goes from 4.6 milliseconds to 16 microseconds and 64 microseconds, respectively. It's not a, amazing benchmark here. I refer to day 1 together with Seva, who told us that, of course, you need to be a little bit more rigorous if you want to have numbers you can rely on. But at least this explains why sometimes maybe my second part may be faster. Why? Because some of the operations I'm using may have already been ever so slightly jitted. That's anyway my guess. Okay, I am now more interested about this language that I hear so much about that doesn't have do-while loops. So from here, I'm just going to take my screen off here. And Vitali, I am very excited to learn a little bit more about what's going on in the Rust world. So I'm throwing you up here, and it's all you. What's going on?
Yeah, thank you. So yeah, here I have Rust Rover, and I am using my own template. I'm trying to do things like this way. So we always have a test data, and we also have a file. So I prefer to have test data in my source code and like real data in the file, but I also try to have uniform processing, right? So I either read this multi-line string here or read from a file. So that's what I usually do. But before actually showing my solution, I would like to show this prepared illustration. So now a little bit more mathematics here. So I'm not that good in drawing right during the stream, so I've prepared this illustration.
Yeah, but your lines are a lot more cleaner, which I prefer a lot.
Well, yeah, I used LaTeX to draw this stuff. So if you look at blue dots here and central segment, those are our antennas. And then green dots, those are antinodes. So my idea is that you don't need to think about those like double the size of vector, stuff like that, because whenever you have 2 points, you always have 1 point on the one side of that segment and then another point on the other side of that segment. So for example, like in this example, we have point number 1, point number 2. And then, of course, we have this vector from one point to another, like this. But what we also have different parameters. Like if you have a straight line in geometry, you can describe it very differently. Like one way was that Seb showed with a vector, and another way is this parametric equation. You have only single parameter t, and if you change that t, you go from one point on this line to another point. So antenna is t equals to 0. Another antenna is t equals to 1. But we also have one, like in part 1, we have anti-dot t equals to -1. And we always have another anti-node with t equals 2. So, like if you look at this picture, it's immediately clear that for every line, straight line that we have with our antennas, we just need to compute 2 additional points on this line for part 1. And then all of the points that happen to be inside the map for part 2.
Mm-hmm.
So, like when I see this, of course, it is very difficult to get this idea while you are solving part 1. But it's immediately clear when you have a full solution for both parts, right? And now it's easier to understand what's going on. So for part 1, we just need 2 additional points to compute 2 additional points on this line. And for part 2, all of the lines. I was trying to solve this problem in Rust. And in Rust, my solution is... it just follows this idea. But in Kotlin, I have another solution in Kotlin because, well, I have Cody here with me in this room, so it was impossible to avoid solution in Kotlin. So I did that. But then I tried to make it much more general than Rust solution. All right, but let me start showing you my Rust solution. So part 1. So this is my like general structure. So what I have here, we have a map. So first I read the map, and map is almost the same as Seb showed. It's like for me it just 2D vector of characters. So very simple map. Then I try to find all of the antennas on that map by using almost the same algorithm. So we can look at them at this algorithm here, find antennas. What I do, just I have empty hash map here, and then bunch of loops, 2 loops, going over rows and then over columns. And with that, I just try to find every cell where we have something that is antenna, so not a dot. And then I just add that to my hash map. So like very, I think it's just the same what Seb did.
I think this is pretty easy to read, even if you're a Kotlin developer. The one thing that I do notice pretty much immediately though is your the syntax for ranges. I think the dot means something else than it does in Kotlin, right?
Exactly. But I think you have already discussed something like that previously in these streams, right? I heard that discussion, right? So the last element is not included here in Rust.
Okay.
So it looks like from 0 to something -1. That's what we in Rust. So right border is not included in Rust.
And what is the syntax for including it? Is it dot equals?
Yes, exactly. So it's like this. So you just say no, what I did here. So you just like this, and then it will be included. Very logical, I think.
Okay. Yeah, it's hard to keep track because I think in Swift it's 3 dots. But yeah, so everybody does it slightly differently. I guess it's one way of introducing a small layer of job security. I don't know.
Exactly. That's what I always think in those cases. Exactly.
Okay, yeah, but apart from this, seems straightforward enough.
So yeah, almost the same stuff. So we are finding all the antennas, and then I'll go back to my part 1. Then I just simple computation for width and height of the map, just to check that we are inside the map at all times. And then I'm looking for anti-nodes. That's another thing. So the general solution, we have our map, then we build antennas, list of antennas, hash map of antennas, and then we're just looking for anti-nodes. And in this find anti-nodes part 1, what I do, once again, I'm building a set because we don't need duplicates here. And then for every kind of antenna, so antennas, it's a hash map. Key is a type of antenna, and then just accept did coordinates. For me, it's just a vector of points for those antennas. And then I go through all the points, all the antennas of the same type. And then I use indices here. And then I go over the second half of the points once again, because I don't need duplications here. So with these 2 loops, I have all the straight lines on this map. So I don't want, so it doesn't matter the way where they look at, like how they turn, doesn't matter. So just all the straight lines, one direction or another. And for every straight line, I do some computations with differences. So just as I think as you did. So this is differences for rows, differences for columns. And then I just add 2 anti-nodes if they happen to be within the map. So at some point, it's just only one of them or both of them.
So here your iteration is essentially you grab the segment, and because you already know, essentially, rather than just creating all possible combinations like I did, where sometimes you have A, B, and BA, and generating 1 point for each of those iterations, what you just do is you iterate in a way that A, B will only appear in this order. You won't even get to BA. But because you know this, you can just add both points at the same time as well, which is a pretty cool approach, actually. Nice.
Exactly. Yeah. So I think that saves a little bit of time here. Maybe not much, but still it saves something. And then, so while I was writing this, yeah, by the way, I should say, so when you see someone's solution, so I think you can be sure that it's not the solution that was submitted first. What I usually do, so sometimes it's some dirty solution and you've got an answer and you submit it, and if it's correct answer, then you try to make things nicer. At least for me, it works this way all the time.
I certainly give it. I give things names for sure. Like names are the big thing.
Names. Sometimes I restructure, I refactor the whole solution to make it nicer. But so this is not the first solution that I have come up with, right? So I am fair here. But when I wrote this part, I was thinking, well, maybe. Like what I don't like here is that I have these 2 almost same if conditions here. So maybe it can be done easier, maybe in one go with both points. So that's what I thought. And then I read the part 2. And at part 2, I decided to implement something like a little bit more general. So let me go back to my parts. So like this was my first part, and almost the same structure for my second part. Like once again, we have a map, we have antennas, we also have width and height, and then we compute anti-nodes. But this way, this is a different function because it's part 2. So, but everything else is just the same. And for the second part here, so what I do, I just, once again, I go over all the antennas. And then I thought, okay, maybe I don't want to have all those 2 loops for building all lines. So instead of 2 loops, I decided to apply this nice function combinations, which comes from itertools library for Rust, which is advanced library for iterators. So sometimes I prefer to use it. So it's not standard library, it's external library, but I still use it for my Advent of Code solutions. It just gives me the same thing, all the combinations for the points. And I don't have to think about repetitions and all that stuff. It just all the combinations, exactly what I need here.
This is fun because just yesterday when we were talking to Olaf, we were talking just about this. It's one of the functions. Combinations and permutations are the 2 functions that are in his little tool belt that he has in his Advent of Code projects as well here. So we see it resurfacing here in your solution as well. Very cool.
Yeah, because like when I was solving all these problems for the first time, when you need combinations, when you need permutations, of course you try to implement it by yourself. But now I know that I will be able to implement it, but it's boring stuff. I don't want to do that once again, right? So that's why I just reuse functions from external library.
Yep.
Which is really ubiquitous in Rust. So that's why I don't have 2 loops here, just these function combinations. One thing that is very different from Kotlin solution that you showed, and you see some bookkeeping here with signed and unsigned integers. That's a really annoying thing in Rust. Because if you have indices or you count something in vectors or somewhere, you always get unsigned integers. But if you need to compute differences, like here, you need to compute differences, you should have signed integers, signed numbers, because it's otherwise you can get overflow very easily. Because with unsigned numbers, you don't have like minus something.
Mm-hmm.
So that's why I need to go from unsigned integers to signed integers to do some arithmetics here. And then I have to go back.
I have a question about this immediately, because of course Rust has safety as one of the big things that I think is always talked about. Is this something that you as the developer need to keep track of, or if you just try to subtract 2 unsigned numbers, you will automatically already get a warning or an error?
Unfortunately, you can get easily runtime error because well, I think they did that for efficiency. They don't control that stuff, so you will get a runtime error if you just if you have like 3 minus 5 for unsigned numbers, you will get runtime error.
Okay.
So
Yeah. I
not
mean,
not
it
very
makes
convenient.
sense. It makes sense if you're doing like some sort of like the offsets into like a memory, or you have like you working with pointers or something like that. You don't want to do like an assigned pointer just so that you can do a minus and a negative offset. I was just curious.
Yeah. Okay. So we have, once again, we have these differences. And now what I'm doing here, I'm computing all the points on the line that I showed you. Like, once again, let's get back to that illustration. So t parameter 0, parameter 1, parameter 2, and so on and so forth. But then also to the negative side, parameter -1, parameter -2. So we have 1, 0, and then 1, -1, 2, -2. Okay, so that's what I'm doing here. So we have this range from 0 to infinity. We'll need to stop at some point, apparently. And then we also have 1 and -1 to go to both directions. So for every number from this range, from every number from this list, we are building our anti-node, which is like by the very, very simple formula here. Then we check that this anti-node is within the map. Then we need to make sure that we've stopped at some point. Whenever in both directions, you see, I go like from 0 to 1 -1, 2 -2. So I need to have both nuns, so both points outside of my map to stop. And then I flatten everything, which either concatenates stuff or removes those options. And as a result, I get some vector of all the points inside the map.
Do I understand correctly that you do one flatten here because you have nested maps, and then you do another flatten because you have an option type, or I guess an option
Exactly.
type. And
Exactly.
so at first you still have a couple of nuns because you might be like running in one direction while you already have exited the map on the other, where you're not generating anything anymore, and you also need to get rid of those. Okay, I get it. Okay.
So, but like the thing is that I compute only once the next anti-node, and I check also only once. So I don't have those two lines like where I check this, check that. I write it once, but then there is a loop that checks everything.
Mm-hmm.
And then I just more flattening because this structure is like really big, and then I collect results. But in the end, I have points for all the anti-nodes. So this is my part too. And when I wrote this, I've realized that, well, it's a little bit upsetting to have all those checks within map. And the reason is that if you have a map, you can easily, or maybe not easily, compute in advance how many points will be inside the map. So you just don't need to generate anything else. So that was my next idea. And then I decided to implement it not here in Rust, in Rastrova, but in Kotlin. But
okay.
One more thing here, by the way, I forgot to show you what I usually do. So of course I always have times. So I have like this 3 milliseconds and all that. But we also have in Rust, we usually have build for development profile and build for release profile.
Mm-hmm.
So I always develop my code in development profile, but it's very easy to switch to release profile. So just this switch here. And when I run in release, it's always just some microseconds. So very quickly, like we can try, for example, now. And then as a result, we get some microseconds. So solution is really quick here.
Very nice.
Yeah. But of course, it's well, for this problem, it's not the, well, it doesn't matter, to be honest, millisecond or microsecond. Right?
Sure,
So,
but I mean, I know this myself. I've played around with Rust a little bit because again, people also say it's like blazingly fast, and you gotta check this out sometimes. And I was like, well, this isn't. I was like, this isn't that fast. And then a friend of mine who I was consulting on this, who I just asked some questions. I was like, why isn't this so fast? He's like, well, have you tried turning on like the production builds? And I think in my example, I saw like a 100x increase, like a 10-second process went down to like 0.1 seconds, something like that. And I'm like, oh, this is fast. This certainly can be fast. Yeah.
So maybe I think we are done here with Rust solution. So unless you have any questions, maybe we can go to Kotlin once again and to show my other solution for Kotlin.
That sounds great. I do want to say here briefly that we have a couple of people saying or having some happiness about the fact that there are infinite sequences or infinitely ranges without an end, infinite ranges, which is very, very nice. We can of course also do that in Kotlin using a sequence generator. But that does involve a tiny little bit of manual work. Okay, I'm going to switch us over back to my screen here, and I'm just going to follow you. But just maybe we can just very briefly, if you want to whip this up, if we had an infinite sequence, then we would just use the sequence builder. In theory, we could also just use something like generate sequence, but quite literally, you could write something like repeat int.max value yield it, and now you have a sequence that happens to go from 0 to like infinity, which is probably exactly what you want. But it would be cool if we had some slightly extra convenience to do the same thing. Okay, so hopefully, Maya, that answers it. Back to you, Vitali.
Yeah, so now my Kotlin solution, but of course, once again, I think it's like, for me at least, it's impossible to come up with this solution unless you already have another solution, right? So just don't think that I'm so smart to have this solution from the first step. No, absolutely not. So in this solution, we have point, right, row, column, and we have this very smart, I should say, class line. So a line is built from starting point and ending point, but I also have this width and height because I needed to build something inside that line. So what I have here, I compute the list of parameters which happen to be inside the map. So how I do that? Like, remember those numbers like t equals to 0, -1, 2, and so on and so forth. So I'm trying to compute the whole range of parameters which happen to be inside the map. How I do that? Well, some calculations, not the best one. You need just to solve a couple of inequalities. Like this point must be greater than 0, and it must be less than width or height. And then you just try to find the value of a parameter. But when, as a result, you can get something like this. Like you start at this point, go to this point. And with these computations, you do that once for every line. But as a result, you always know for which values of parameter your point will be inside the map. So you don't need to compute something and then check. You always know which parameters correspond to points inside the map.
And of
That's
course,
an idea.
it's worth pointing out here again explicitly. I think it's heavily implied here, but there's obviously no loops inside calculate range. Like you just solve an equation, like you just do one calculation, and that just gets you to where you need to be. So it's not like you introduce an extra iteration or anything like that. It's a cheap operation to do in advance.
Yes. Once for every line, no loops, just very simple computation. But to be honest, it took me like at least an hour to come up with the right formula with all those like -1 and +1 and all that stuff. So it was not an easy walk for sure. But like as a result, I've got this class, and this class is able to get me point based on the value of a parameter. I just compute it if it happens to be inside those parameters, and it's just a range. So it's also a simple inequality here. Then I just return this point, 1 point of the line. And with this class, which is able to figure out quickly point inside the map and outside, I've got this main function. It's almost the same, and actually both parts are solved with a single function solve. Once again, I have all the antennas. I have list of lines, and for list of lines, I go over all the antennas and build those lines from every couple of points. And then, like the core part of the solution is this filtering. So I have this parameter predicate, and I just based on that predicate, I try to compute what I actually need for first part and for the second part. So I just go over all the parameters, all the points inside the map. So I don't compute anything else, and filter out those which I don't need. Like in part 1, I need only 2 points. And in part 2, I need all the points. And this is what I'm doing here. In part 1, I'm solving my problem with 2 points, -1 and 2. Those are like before and after my segment.
Yep.
And in part 2, I just say true because I need all the points. And then, so I just don't need to filter out anything. And that's it. So that's the full solution for this problem. Much like less loops here. I didn't try to measure efficiency because, well, you still need to read all those antennas and lines, but at least you don't need to compute useless stuff that will happen to be outside of the map. So
yeah,
that's my Kotlin solution.
And you've made it very nice in general. So if now you would like to know the solution given like 3 more like resonances or something rather than the entire map, that's a matter of like just switching out the one parameter in your or changing the parameter to your solve function, and you have all of that with the same runtime complexity, which is I mean, it's very elegant. I like this. I've definitely learned something. I've learned something new here, which is taking maybe like one step back sometimes and seeing if it's not worth thinking about segments and I guess those parameterized equations rather than just immediately going to point in a plane, that's a vector. Everything's a vector now.
Yeah, but that's what we do in mathematics. So sometimes we need vectors, sometimes we just work with points. So both methods, of course, are very legible. So
Yeah. No, this was really cool. I mean, not only did we get to see an entirely different programming language, we also got to see a whole bunch of different solutions for the same problem, which, I mean, that's always a delight. So yeah, thank you so much, Vitali, for coming on today and showing us all of this and, you know, preparing these solutions. I think that was very well explained as well. So appreciate it.
thank you very much for having me.
If you have kind of gotten a taste for Rust today, then of course I want to shout out once again that Rust Rover, the IDE that we build at JetBrains, that makes it nice and easy to work with Rust code, is free for non-commercial use. So if you just want to try something yourself or want to validate some of the code that we saw today on stream, then just grab yourself a download of Rust Rover, which again is free for non-commercial use. I'm also going to put the little link here in the description. And whether it is whether you are writing Kotlin code or whether you're writing Rust code, we have actually 2 different campaigns running at JetBrains at the given time. We are on the Kotlin YouTube channel, so maybe we have a little bit of a home advantage here. If you do have a couple of solutions in Kotlin and you would like to win some exclusive Advent of Code swag, make sure you check the blog post that we linked earlier about that. And yeah, apart from that, thanks again, Vitali, for coming on. And thank you to everybody who decided to spend their Sunday evening, potentially, depending on your time zone, with us. It was a wonderful, cozy time with a little bit of puzzling and a little bit of learning. So I'm quite excited to, get to solving a new puzzle in probably close to like 12 hours now. It's not that long. No, just 11 hours remaining. So yeah, of course, our campaign will continue running. So you can go to youtube.com/Kotlin, go to that live tab, and make sure you hit all those little notify buttons for the remaining 4 streams, because we still have some pretty cool things coming up. Tomorrow, we'll be doing some Compose multi-platform stuff. Hopefully, at least my guest is going to be very well versed in that subject. We'll see. Maybe we're lucky to get something that can be visualized nicely. Apart from that, maybe we'll just play around with some Compose anyway. Yeah. So best of luck to all of you who will decide to solve tomorrow's puzzle, and enjoy the rest of your day. Happy Advent of Code, and see you tomorrow. Bye-bye.